actually more than 50 slides, so that could be a bit longer session today. And of course, since Alicia is not here yet, there is the chance to talk a bit longer. So, but I will try to at least roughly be in time with the finishing of the lecture. Okay, so what we discussed yesterday was the fundamentals of modeling thermonuclear explosions of white dwarfs. We actually discussed the matter in white dwarfs, the properties of matter in white dwarfs. We discussed the structure of white dwarfs, and then we set the foundation for modeling explosions in them by discussing the equations of reactive fluid dynamics yesterday. So now this can be applied to now try to understand how thermonuclear burning in white dwarfs really works, and this is actually the plan of the lecture for today. So I will talk about thermonuclear combustion and the burning processes that happen during thermonuclear explosions of white dwarf stars. Okay, so that's the topics for today's lecture. So I will talk about thermonuclear combustion first, and first give a rather general introduction what combustion fronts really are, and then we will actually take a look at what these combustion fronts, or how these combustion fronts are realized in white dwarf matter as deflagrations and detonations. And then in the second part of today's lecture, I will talk about the nuclear burning processes in exploding white dwarfs. We will take a look at the burning regimes, the nuclear statistical equilibrium that is reached at the highest densities, and I will also mention a metallicity effect that has a rather large impact on the nuclear synthesis and the brightness of the events in the end. Okay, so let's start out with some general remarks on combustion. So if you look up the term combustion on Wikipedia, you will find this explanation here. Combustion or burning is the sequence of exothermochemical reactions between a fuel and an oxidant, accompanied by the production of heat and conversion of chemical species. So this is very much tailored to terrestrial and chemical combustion. But of course you could just remove all the terms from that definition that refer to chemical reactions, and then you get a more broader or more general view on combustion. Such processes are quite widespread in nature, so a lot of phenomena can actually be cast into combustion. There are even some people from the combustion community who would claim that the entire universe can be described as a combustion system, but this is a bit far-fetched perhaps. But at least for our purposes of describing thermonuclear explosions, the concept of combustion is very useful. Now, the characteristics of different combustion processes in nature vary significantly. Again, looking into chemical terrestrial combustion, one can find different classes of combustion processes depending on how the reactants are brought together in the fuel. So one possibility is what the combustion engineers call premixed combustion. So here the idea is that all the necessary ingredients for the reactions are contained in the fuel mixture already, and then there is non-premixed combustion. So this is where diffusion processes are required to bring the reactants into contact. If we think of thermonuclear combustion in astrophysical environments, of course, then the fuel material contains all the species because these are nuclear reactions, and therefore the processes we are discussing here resemble premixed combustion, as the combustion engineers would call them. All right, now combustion fronts. So combustion is usually ignited at in a certain volume, so localized in space, and spreads out from there. So reactions propagate and spread out from there. And in thermonuclear supernova, we find the particular feature that the reactions are extremely dependent on temperature. So the thermonuclear reaction rates, except for the example of carbon burning, for instance, in the regime we're interested in at temperatures of, say, a gigakelvin or so, scale with the 20th power of temperature. So that means that the reaction really takes place only at the very localized conditions where the temperature is absolutely highest. So they are localized in space and confined to a very thin layer. So therefore, these reactions are expected to propagate as thin combustion waves through the white dwarf material. Okay, so Combustion waves in white dwarfs are characterized as such. So at high fuel densities, the width of these combustion waves is very small because of the very high temperature sensitivity of the reaction. It is less than millimeters. Then, of course, the front propagates from the ignition near the center of the white dwarf outwards. The material expands, and therefore the fuel density gets lower. This leads to a broadening of the combustion waves, but they are still small compared to the scales of the exploding white dwarf. So the white dwarf, of course, has in the beginning a radius on the order of 1,000 kilometers, and it is expanding. So therefore, an idealized treatment of a combustion wave can be used, where we describe this combustion wave as a sharp front that separates the fuel from the ash, and we assume that inside this sharp front there's an instantaneous conversion of fuel to ash, and the energy is instantaneously released. And this is actually an excellent approximation for combustion modeling on large scale. So if you want to describe how a reaction wave propagates through a white dwarf star, such an idealized treatment as a sharp front is a good approximation. So that's the so-called discontinuity approximation, which provides the simplest model for a combustion wave. Of course, if we assume that this combustion wave is just a sharp discontinuity, we do not resolve the internal structure of that wave, and we do not resolve the details on how the material is really converted from fuel to ash. However, it is still possible in this discontinuity approximation to derive the correct relation between the hydrodynamical states in the fuel and the ash. Now, this treatment as a discontinuity simplifies, of course, the equations. I gave you the full set of equations that is necessary to describe all the details of combustion front propagation yesterday, including the reactions and the transport terms. But of course, if we simplify the picture to the discontinuity approximation, then we neglect all these microphysical details. So the transport by diffusion and heat conduction is neglected. Yeah. Okay, so this is actually what we will start out our discussion with. So we start out with the discontinuity approximation. We assume for simplification in ideal fluid, we will not, for the beginning at least, look into external forces, so gravity and other external forces will be neglected for the first part of the discussion, so that we actually restrict the system that we consider to the Euler equations with just source terms due to reactions. We will actually do our treatment in the frame of reference of the discontinuity, so we will fix our coordinate system to that discontinuity, and it will propagate with the discontinuity. So we will then therefore measure velocities relative to the discontinuity, and this is done here. So U means this is the normal velocity with respect to the discontinuity in the unburnt material, and UB is the velocity with respect to the discontinuity in the burnt material. Okay, if we want to model combustion as sharp fronts, as discontinuities, we encounter immediately a problem from what we discussed yesterday. And this is, yesterday I set up the equations of reactive fluid dynamics in differential form. Now, PDEs, so the conservation laws in differential form, will allow only for continuous solutions, for smooth solutions. But they, so these are called the strong solutions, but of course these differential laws don't actually allow for weak solutions. And weak solutions are solutions that contain jumps and discontinuities, and this is what we're interested in here. So therefore, one has two ways to approach the problem. Either one starts out the discussion directly from the integral form of the equations of fluid dynamics, because they are more general. They allow also for discontinuous solutions, for weak solutions. Or we augment the set of differential equations that we discussed yesterday by additional jump conditions that relate the hydrodynamical states on both sides of the discontinuity. So jump condition, this is a little bit similar to what we actually also learn in electrodynamics. So I will first discuss how this is done, how we set up these jump conditions on a simplified system, namely on a system which is not really a combustion, because for the first part of the discussion we will neglect reactions. So we just look into the pure hydrodynamical system, and in that, of course, we have conservation of mass, momentum, and energy, as we discussed yesterday. And in a discontinuity, in a jump of hydrodynamical quantities, these quantities should still be conserved. So that means we expect continuous fluxes of mass, continuous fluxes of momentum, and continuous fluxes of energy over the discontinuity. They may, however, carry jumps in other hydrodynamical quantities. For instance, there is, of course, a jump in density, in temperature, maybe also a jump in pressure. But the fluxes of the conserved quantities of mass, momentum, and energy should be continuous over the fluid. And this gives rise to the jump conditions over fronts. So from the conservation of mass flux, momentum flux, and energy flux over the discontinuity, one can derive these jump conditions. So the first continuity is the continuity of mass flux, expressed in our coordinate system relative to the discontinuity. We have that the mass flux in the unburnt material, so this is just the density in the unburnt material, or the, say, in the material ahead of the discontinuity, which I denote here with the index 1, times the velocity in that material, equals the mass flux on the other side of the discontinuity, ρ2 U2. So this should be the mass flux, and I denote this mass flux with a capital M here. Now, depending on the value of this mass flux, you can distinguish two kinds of discontinuities. So one is, of course, this equation holds if the mass flux is simply 0, if we don't have a mass flux over the discontinuity. And then we have a contact discontinuity, or in multi-D this is called tangential discontinuity. We're not interested in this solution here. We're interested in the other case, that we do have a mass flux over the discontinuity, because if we have burning, then of course we will actually convert mass in the burning front, and mass will be transported over the discontinuity. And this is actually a shock wave. So a discontinuity, a hydrodynamic discontinuity with mass flux over it is called a shock wave. So we can specify the properties of that shock wave in a very nice graphical representation if we look into the properties in the plane that's spanned by pressure and volume. So here on the y-axis I have pressure. On the x-axis this is volume. I denoted it with tau. So tau is just 1 over density, so this is specific volume, volume per mass. But you could also do this in terms of normal volume. That's it's just easy to derive the relations in terms of specific volume. Okay, so that means that we can specify in this plane here the initial state ahead of the discontinuity that's characterized by the hydrodynamical quantities by pressure 1 and specific volume 1. So this characterizes the state ahead of the shock front, P1, tau 1. Okay, now from continuity of the mass flux over the discontinuity, so you can actually look into the Euler equations that I gave yesterday. You will see the terms that specify the momentum flux over the in these equations. The momentum flux is just given by rho times u squared in the one-dimensional treatment plus pressure. So pressure gives you a momentum flux, and density times velocity squared is also momentum flux. So this quantity on both sides of the discontinuity should be conserved, and for brevity, actually I introduced the abbreviation here in this bracket notation. So this bracket notation here means the difference between the quantities on both sides of the flame of the shock wave. So rho u squared on the state ahead of the shock with index 1 minus the state behind the shock. So this is just a shorthand notation. All right, from that you can directly get the so-called Rayleigh criterion. So this continuity of mass flux over the discontinuity over the shock wave gives you a relation between the state in terms of pressure and specific volume behind the discontinuity in terms of the initial state. And it's related as here as a linear relation, and the coefficient of the linear relation is minus mass flux squared. So that means this conservation of momentum flux over the discontinuity specifies all the possible post-shock states, and these possible post-shock states must lie on a straight line that issues from the initial pre-shock state and has a slope of minus m squared. So this is called the Rayleigh line. One thing to note here is that the slope of that line is always negative, because m squared is of course a positive quantity, and we have the slope being minus m squared. So this is of course a purely mechanical relation, so that's derived by momentum flux. So that means that for a given pre-shock state, the Rayleigh line specifies all mechanically possible post-shock states, and they all lie on this straight line through the initial conditions with slope minus m squared. So now let's do the same thing for the energy flux conservation. So we can write down energy flux conservation in the same way, read off the terms from the Euler equations that specify the energy flux. You will find this expression here, and this has to be the same on both sides of the discontinuity. Now this gives you another relation between the pre-shock states and the post-shock states, and this is expressed in this way here, and what you find is the so-called Houguerot adiabatic. So this is the curve that I marked in red here, and this curve actually specifies all potential or all possible post-shock states. They have to lie on that curve that are thermodynamically possible, because now we actually considered the thermodynamics, we considered the energy. So that means from the first relation, the Rayleigh line, we got for a given pre-shock state all potential mechanically possible post-shock state on that straight line, and from energy flux conservation we get all thermodynamically post-shock states, possible post-shock states on that Houguerot adiabatic. So that means that the physical post-shock state, that should be of course mechanically and thermodynamically possible, is just the intersection of these two, and this is actually what we find here. So we can, in this representation, from this graphical representation, directly read off for a given pre-shock state what the post-shock state is. So this is just the intersection of the Houguerot adiabatic with the Rayleigh line. Okay, now, so what changes in this picture if we introduce reactions? So this was pure hydrodynamics, this was just pure shock relations. So now, let's see what changes if we introduce reactions. Reactions, as we discussed yesterday, have no direct effect on the momentum balance law. However, they change, of course, the energy equation, because we have an energy release in the reactions. So that means that the Houguerot adiabatic will change, and it will change by adding another term. And this term is just the difference in the formation enthalpies of the burned and unburned material. So this is actually reflecting the heat release in the reactions. And then the Houguerot adiabatic changes into what is called the detonation adiabatic. This is just adding one term. And the effect of this is that the Houguerot adiabatic will be shifted upwards here. So it will now be shifted from this initial state upwards and will not intersect anymore with the initial state. So we are talking about burning here, so that's why I now denote the initial state with P and tau U as standing for unburned. Okay, so that means we have found another condition that derives from energy flux over the burning front. As said before, momentum flux is unchanged, so therefore still the same Rayleigh line applies. And again, we get the burn state behind the combustion front from the intersection of the detonation adiabatic that is now shifted upwards with respect to the initial state, and the Rayleigh line as before. So this has still the slope of minus m squared, and the intersection of these two again specifies the burn state behind the combustion front. Now the slope of the Rayleigh line, as said before, must be negative because it's minus mass flux squared. So that means the slope of this blue line here, the Rayleigh line, always has to go in this direction. It cannot actually have a positive slope. So that means that these gray or light blue areas here cannot be reached. Okay, so that means that the potential post combustion wave states, the burn states, can lie either on the upper branch of the detonation adiabat or on the lower branch. So this divides the detonation adiabat into two branches. Here, this part cannot be reached in this gray area, but the upper branch can be reached and the lower branch can be reached because the Rayleigh line always has a negative slope. Okay, now from looking into this closer than I actually can discuss this here in the amount of time I have available, one can also make an argument about the velocities of this combustion point. So one finds that the speed of sound in the unburnt material corresponds to the slope of the tangent to the Houguenot adiabatic in the unburnt state. So that means in the upper branch we can measure the slope of the Rayleigh line, and it will always be steeper than the tangent to the Houguenot adiabatic. So that means that in the upper branch, because of the steeper slope, the combustion wave with respect to the unburnt state will be faster than the speed of sound. So that means it will be supersonic. And this is why the upper branch of this detonation adiabat is associated with the phenomenon of detonations. So these are combustion waves that propagate with respect to the unburnt material supersonically. The lower branch, for the lower branch the opposite holds. So here we always have a shallower slope than the one that would actually specify the speed of sound with respect to the unburnt material. So therefore here we have subsonic combustion waves propagating with subsonic velocities, and these are deflagrations. Okay, so this is the discontinuity picture of combustion waves, the discontinuity approximation. So I've shown you that just from considering the jump conditions over discontinuities, we can derive relations between the burnt and the unburnt states. However, this does not explain why such combustion waves propagate on a microphysical level, a microscopic level. So what's really the physics that makes these combustion waves propagate? Now, if we take a look into the microscopic structure that's schematically shown here, we get the following picture. For deflagrations, for the subsonic combustion mode, we find that the propagation is due to microphysical transport processes. So the idea here is that the energy that's released by the reaction is released in the so-called burning zone. So here is a schematic sketch of the quantities inside the deflagration wave if you don't actually treat it as a discontinuity but resolve it. So this is a reaction wave that propagates to the left, from the right to the left. And here we have the reaction rate going up and material is converted. So this is called the burning zone. And out of this burning zone, we have conduction and diffusion of heat in the fuel ahead of this zone. So we heat up material here, so the temperature goes up ahead of this reaction zone. So this heats up the material so that the fuel material at some point, because of the heating, also reaches a state where it starts to burn. And this actually makes deflagrations propagate as a flame front. So we can actually distinguish two zones inside such a deflagration flame. The zone where the burning actually takes place, this is the burning zone, and the zone ahead of it where the material gets heated due to heat conduction out of the burning zone, and the fuel is then heated and at some point also will start burning. This is called the preheat zone. Now, obviously, because the propagation is due to the heat conduction from the reaction zone into the preheat zone, the speed of the propagation of such a structure is set by the microphysical transport processes, by the heat conduction, by the diffusion, and therefore it's a slow process. Now, this is just a schematic picture. The full structure results, of course, from solving the equations of fluid dynamics with all the source terms included that I discussed yesterday. So you need reactions and you need the transport terms that I discussed yesterday. Now, deflagrations in white dwarf matter are more complex than this schematic picture would suggest. The relevant microphysical processes, of course, all have to be modeled. Species diffusion, heat conduction, and so on has to be modeled. Nuclear burning also is not as simple as in the schematic picture because it involves a multitude of reactions. We have carbon burning, oxygen burning, and silicon burning, and may reach nuclear statistical equilibrium, which I will discuss later, if the fuel material has high enough density. So we have different reactions taking place inside the burning zone. The energy transport is mainly due to thermal conduction. And the energy flux is then caused by a density gradient as here. Now the proportionality factor is the thermal conductivity, and the value of the thermal conductivity, of course, is set by the transport properties of the different carriers. So we can actually have thermal conduction due to electrons, ions, and photons. And this has to be determined in white dwarf material. So what do we find for typical conditions in white dwarf stars? Well, it's not very surprising, but what you find is that electron conduction dominates over all other effects. The reason for this is easy to understand. The final states for electronic scattering are occupied below the difference between the Fermi energy of the electron gas and its thermal energy. Fermi energy is about 1 MeV and thermal energy is about 10 keV. And that means that most of the states that an electron could scatter into are already occupied, and therefore we have extremely large mean free paths of the electrons in degenerate material. So that means that we have very high thermal conductivity due to electron transport in white dwarf material. So this has implications for deflagrations in white dwarf matter that makes it distinct from deflagrations that we have in terrestrial combustion. So therefore we talk for quite a while with engineers, and they always think about the terrestrial combustions, but the conditions there are very different. So the way actually they talk about these characteristics of such transport processes and combustion processes is that they do that in terms of figures of merit that then would reflect, in our case, the efficiency of the electron conduction. So we actually introduced such a figure of merit yesterday when we introduced the Reynolds number. This compared the inertial term in the Navier-Stokes equation to the viscous term, and therefore gave us an idea of how strong turbulence effects are. Now here you introduce other figures of merit to compare other effects. So one of them is the so-called Lewis number. So the Lewis number compares the magnitudes of thermal conduction and diffusive energy transport. And for terrestrial combustion, one usually has Lewis numbers that are on the order of 1. For white dwarf matter, as we discussed, electron thermal conduction due to electrons is totally dominant, and therefore the Lewis number is very large. So we typically have Lewis numbers of the order of 10 to the 7 in white dwarf material. Another dimensionless number that characterizes burning in white dwarfs is the Pronto number. The Pronto number compares viscous transport to thermal conduction. For typical white dwarf matter, one of course finds again that viscosity is low and thermal conduction due to electrons is very high. So therefore these Pronto numbers that we typically get here are very small, 10 to the -3 or something like that. So what's the consequence of that? Well, the huge Lewis number means that diffusive processes are unimportant for the energy transport and can be neglected from our system. The low Pronto number means that the viscous effects are subdominant, and this is again an argument for using the Euler equations instead of the full Navier-Stokes equations. Okay, now this specifies which kind of system you have to solve if you want to get actually the full structure of a deflagration, you can do that numerically. So there are several studies of deflagrations in white dwarf material that have solved these equations fully numerically. And this is done actually with the aim of determining the typical propagation speed and the width of the structure of such a deflagration flame. And what people look into there, of course, is the laminar case. So that is, we have a planar, undistorted flame, and we ask the question, if we have this planar, undistorted, geometrically undistorted flame, how fast does it propagate and how wide it is it? And this can be then given the laminar flame propagation speed as L and the flame width LF as a function of the fuel density, the temperature, and the composition of the fuel material. And if you are interested in the values, there's a rather extensive study of this given by Timmis and Woosley in 92. So the important thing that one finds here is that typically with lower fuel densities, the laminar flame speed will decrease and the flames will become wider. So the flame width goes up. So here's an example of a numerical simulation that my former diploma student Philip Edelman did. So this is a somewhat strange condition. So this is at 4 × 10⁹ grams per cube centimeters at rather high fuel densities. And we have a composition of the white dwarf material of 30% carbon and 70% oxygen. And you see a typical structure that you get from such numerical simulation. So here we have in green, the density that goes up over the flame. We have the temperature that goes up. The density goes down and temperature goes up. Propagation direction is in this direction towards the right. And here we have the different species, and you can see, if you consider a full network with different reactions in it, that the conversion between the different species takes place at different locations. So at the point where the heating is highest, we have a conversion of carbon. So carbon is depleted here, and then only later silicon comes up, and very much later iron group elements are produced. Okay, so this is the picture of a laminar flame, a geometrically undistorted planar flame that propagates into the fuel. However, if you look into more than this simple 1D picture, there are various instabilities that become important for the propagation of flames in white dwarf material. So some of them are relevant or even fundamental for thermonuclear supernovae, and in particular this is of course the case in scenarios where we have deflagrations. So this is a possibility for burning in Chandrasekhar-Mars white dwarfs, as we'll discuss probably tomorrow. Not all conceivable flame instabilities, however, are relevant. So there's something called the thermodiffusive instability, and this is usually suppressed at the high Lewis numbers that we have here. So I will discuss therefore the 3 main instabilities that we have under conditions of deflagrations in white dwarf stars, and these are the Rayleigh-Taylor instability, the Kelvin-Helmholtz instability, and the Landau-Dayeux instability. So let's start out with the Rayleigh-Taylor instability. So this here is supposed to be a movie, and I'll see whether I get this started. Yes. Okay, so this is simulation by Volker Springer's group at the Heidelberg Institute of Theoretical Studies. So Rayleigh-Taylor instability is actually due to hydrodynamics with gravity, so we have to include Suess terms to see that here. So we have gravity pointing in this direction, and we have an inverse density stratification in the gravity field. So that means we have the dense the dense material above the lighter material. And if gravity is pointing downwards, this will give rise to instabilities. So initial perturbations then start to grow as here, and what you typically see is that this instability leads to these mushroom cap-like features. So this is typical for the Rayleigh-Taylor instability. So this is a buoyancy instability that results from an inverse density stratification of material in a gravitational field. So this is a case that we find in burning in white dwarfs. So because burning starts near the center of white dwarfs and leaves behind light and hot ashes, in which the degeneracy is partially lifted. And this then leads to an inverse density stratification in the material, which is unstable to buoyancy, and then these typical mushroom cap-shaped plumes of burning material develop in the nonlinear stage and then rise into the fuel. Now there's this, another instability that's important. That's the Kelvin-Helmholtz instability. So I again have to restart the movie. The Kelvin-Helmholtz instability is actually an instability that comes about due to shear. If we have two fluids that have a shearing motion, so the sludge fluid goes into this direction, blue goes into the other direction, then small perturbations at this interface will grow and in the nonlinear stage form these typical eddies that you see here. Now, in our situation of deflagrations and white dwarf stars, this is a secondary instability. So the shear instability, Kelvin-Hamilton instability, amplifies initial perturbations in shearing fluids. It forms a wave pattern, and then in the nonlinear stage, these typical whirls, these eddies are generated. And it's a secondary instability because it happens at the fuel-ash interface in the case that we have bubbles of material that rise due to Rayleigh-Taylor instability. Then we have shear motions at the edges of these Rayleigh-Taylor instabilities, and at these edges then the Kelvin-Hamilton instability will become active and create these eddies there. Now the third instability I wanted to mention here is the Landau-Eu instability. I will not actually go much into detail about this here. This is an intrinsic flame instability, not something that is caused by an external effect such as shear or gravity as the other two instabilities, but this is intrinsic to the self-propagation of the flame. It is active on scales that are significantly larger than the flame width, where the flame can be, again, treated in the discontinuity approximation. You can actually nicely explain how this works in detail, but I will not do that here in detail, but just mention that the reason for this instability is the self-propagation. So this is caused by the refraction of streamlines in the vicinity of the flame due to the density jump we have over the flame. Now the important thing here that I wanted to mention is that the Landau-Eu instability is an instability that stabilizes itself in the nonlinear regime. It forms a cellular pattern, but then it stays stable in the cellular pattern. And so this was already suggested in the 1960s. In my PhD work, I actually also looked into this with numerical simulations and found that actually this self-stabilization works also under the conditions that we have in thermonuclear supernovae. So therefore, the Landau-Eu instability is thought to have no significant impact on the burning, the burning on large scales. And this is different for the other two instabilities. There's no nonlinear self-stabilization for the Rayleigh-Taylor and the Kelvin-Hamilton instability, so therefore they are fundamental for the evolution of the flame structure on scales of the white dwarf star. And they lead to significant acceleration of the burning in thermonuclear supernovae. So this is a very important effect to consider if you model deflagrations in white dwarf stars. And the overall effect in, of Rayleigh-Taylor and Kelvin-Hamilton instabilities in a reactant fluid was simulated on this microscopical level by Mike Zingali with the Low-Mach number code. I just wanted to show the result here to give you an impression of how this looks in 3D. So this is the simulation. You see the Rayleigh-Taylor instability to develop with these mushroom cup-shaped features. And then secondary instabilities will, secondary shear instabilities will lead to a more complex structure. And in the end, you get the production of turbulence by Kelvin-Hamilton instability, and you get a rather complex flame surface. So this is a flame surface subject to buoyancy that you see here. Okay. Okay, so one question to consider is the Rayleigh-Taylor instability active on all scales? So is the fluid or the situation unstable on all scales? In order to find out, one has to compare the growth time of the Rayleigh-Taylor instability, which you can get from a linear stability analysis, with the burning time scale. And there's a competition between these two in the following sense. So on the smallest scales, one finds from linear stability analysis that perturbations with small small perturbations with small wavelengths will grow slowly due to the Rayleigh-Taylor instability, and they will be too slow to compete with the flame propagation. So they will just be overrun by the flame. So that means that at the smallest scales, the Rayleigh-Taylor instability will not be active. The growth time of the Rayleigh-Taylor instability, however, increases decreases with the length of the perturbation. So this is spelled wrongly here. So this develops quicker if you go to larger scales. So therefore, there will be at some point a scale where the Rayleigh-Taylor instability wins over the flame propagation. So this minimum scale for Rayleigh-Taylor to develop in the presence of a self-propagating flame is called the fire polishing length, and you can actually give an expression for that. So the Rayleigh-Taylor instability is only active above a certain length scale. The Kelvin-Helmholtz instability is important in thermonuclear supernovae because this is actually what in the end, in the nonlinear stage, leads to the generation of turbulence. One can make an estimate by comparing the typical velocities of a buoyantly rising plume that sets the velocity of the shearing layers where the flame is located, and we would take the typical length scales and the typical viscosity of the material, and then you get an estimate for the Reynolds number, and you find that the Reynolds number is huge. It's 10 to the 14 in the case that we expect in deflagrations in white dwarf material. So that means that turbulent eddies will be generated by the that should be Kelvin-Helmholtz Kelvin-Helmholtz instability at the flame on the largest scales by the buoyant plumes due to the Rayleigh-Taylor instability. So these eddies that are generated by the Kelvin-Helmholtz instability are unstable, and they decay to smaller scales, and in this way a phenomenon forms that's known as the turbulent cascade. So the idea here is that these Kelvin-Helmholtz induced eddies act on large scales. They are unstable, they decay to smaller and smaller scales, and this transports turbulent kinetic energy from the large scale where it's injected by the instability to smaller scales without without energy loss through the so-called inertia range. And the eddy velocity, however, decreases towards smaller scales, so that at the Kolmogorov scale, you will find that the local Reynolds number at the small scale with the small velocities and the small scales will at some point be 1, and then viscous effects dissipate away the turbulent kinetic energy into heat. So this is the concept of a turbulent energy cascade, and this actually has significant impact on the flame. So the flame interacts with turbulence, strong turbulent eddies will affect the flame structure. They will corrugate and wrinkle the flame. So on large scales, we have a deformation and a corrugation of the flame front due to the interaction with turbulent eddies. The question then is, down to which scale does the turbulence interact with the flame? So the reason for this question is, again, similar to the argument of the fire polishing length. Below some scale, the turbulent eddies inside the turbulent cascade become smaller and smaller towards smaller scales. So therefore, below a certain scale, they will be very slow, and then they can be overrun by the speed of the laminar flame. And the scale at which this happens, at which the turbulent velocities are on the order of the laminar flame propagation speed, so that the flame then can overrun the turbulent eddies, or the flame propagates through turbulent eddies before they can actually turn over, is called the Gibson scale. So only down to the Gibson scale, turbulence has an effect on the flame. So below the Gibson flame, the flame is nearly undisturbed by the turbulent eddies because they turn around so slowly that the flame burns faster through them than they actually than the flame notices any effects by the turbulent eddies. Now this is important for thermonuclear supernovae. So if we assume constant turbulent eddy velocities, then of course we have, as we stated before, that the laminar flame speed decreases for lower fuel densities, and that means that the Gibson scale will become smaller and smaller. So that means that if we go to lower fuel densities, as will happen as we propagate with the flame from the center of the white dwarf outwards, and as the white dwarf expands, the fuel density will drop, the flame speed will become lower, and therefore the Gibson scale will become lower. And this is actually illustrated here. So this is the Gibson scale for different fuel compositions as a function of fuel density. And it goes down with fuel density. And it's important to determine how far down the flame turbulence interaction really reaches. So what is the size of the Gibson scale compared to the width of the flame? So why is this important? Well, we have in principle two cases. One case is that the Gibson scale is larger than the flame width. So if the Gibson scale is larger than the flame width, it means that turbulence will not interact with the internal structure of the flame. So that means it will still corrugate and wrinkle the flame as a whole structure. And of course, this will then enlarge the flame surface area, and therefore the burning will become more efficient and the flame will accelerate, but the internal structure of the flame will be unaffected. So we still have locally the propagation of the flame with its laminar value. And this is called the flamelet regime of turbulent combustion. So we only have a corrugation of the flame on large scales, but the turbulence does not interact with the internal structure of the flame. So that means the microphysics of the burning, the energy transport inside the preheat zone and so on is unaffected. So that means locally the laminar flame speed is unchanged, but of course the overall wrinkling on a large scales has a significant effect on the burning efficiency, because the overall flame surface area increases dramatically due to the turbulent eddies, and this of course leads to a higher net burning rate, and the flame will accelerate significantly. The other case is that the Gibson scale is smaller than the flame width. So that means that now turbulent eddies can have an effect on scales inside the internal structure of the flame. So this here is wrong. This here should be crossed out. So then we enter what is called the distributed regime of turbulent combustion. And here turbulent eddies transport material into and out of the flame front structure and may even disrupt it. One can distinguish between different sub-regimes, so the so-called thin reaction zones regime, where turbulence actually alters the structure of the preheat zone only, but not yet the reaction zone, which is usually much thinner. Then when the Gibson scale reaches the width of the reaction zone, then the flame surface area increases and the net burning rate goes up, and we enter the so-called broken reaction zones regime. And finally, at some point, turbulence may actually completely dominate the internal structure of the flame, and one cannot then talk about a coherent flame structure anymore, but turbulence completely disrupts the flame and spreads it out over space, and then we are in a regime that's called the well-stirred reactor. And this, of course, will at some point happen at very late stages of the burning in a exploding white dwarf. So in the beginning we have high fuel densities, then we are in case 1 where turbulence does not interact with the internal flame of the internal structure of the flame. We are in the flamelet regime where flame is corrugated and accelerated, but internal structure is unaffected. And later on, at lower densities, we may enter the distributed regime of turbulent combustion. So this is the situation in type 1a supernovae. We start out at high fuel densities where the laminar flame speed is high, the Gibson scale is large, the laminar flame width is small, and therefore burning happens in the flamelet regime for most of the explosion. And only at the end of the burning, turbulence freezes out due to expansion, but before that happens, at fuel densities of about 10 to the 7 grams per cube centimeters, we have a transition of the flame from the flamelet regime into the distributed burning regime. Okay, so the message to take away from this consideration of instabilities and turbulence is that deflagrations in thermonuclear supernovae are far from being laminar. We have a pronounced multidimensional structure due to instabilities and the interaction of the flame with turbulence. So therefore, 1D models cannot capture the burning physics consistently. And this is actually the reason why the flame speed has to be treated as a free parameter in one-dimensional thermonuclear supernova models, and it's not actually a self-consistent quantity that comes out of the model. A self-consistent treatment requires multi-D simulation approaches. Okay, now detonations. The microphysical structure of a detonation is very different from that of a deflagration that we have here, and this here is a detonation. So in a detonation, the propagation is due to the progression of a shock wave that compresses and heats the material, and so that it actually becomes hot enough so that it starts burning. The burning in turn releases energy to further support the shock wave. So it's not only a shock wave that propagates through the material, heats it up and burns it, but also the burning itself releases the energy to make the shock wave propagate further. So this is sort of both requiring each other. Okay, so in the shock wave, of course, pressure and temperature go up. That means that the reaction rate goes up. So this is what we see here. So this is the shock wave. The propagation of the flame is in this direction from the right to the left. So we have the shock here in front that actually heats up the temperature as here, and the pressure goes up. and this actually makes the reaction rate also to increase, but it increases slowly because the shock is usually too thin to allow for complete burning, and the reactions take place in a rather extended zone behind the actual shock. So reactions are behind the shock until the fuel is ultimately consumed. So this is your fuel mass fraction. It actually goes is nearly unaffected in the shock itself, and only later it gets slowly depleted. An important consequence of this is that the propagation of a detonation is not determined by microphysical transport processes, but by hydrodynamical effects, by the propagation of a shock wave, and therefore it is supersonic. One can understand the internal structure of detonations in more detail, even within the discontinuity approximation, because it's a hydrodynamical effect to first order, and this idea is followed by the so-called ZND model. That's the Dawes von Neumann-Döring model. So the idea is that one still treats the shock wave as infinitely thin as a discontinuity, so therefore we can actually illustrate what happens again in our pressure volume diagram with the detonation adiabatic and the Rayleigh lines as we had it before. So we start out in our initial state A here, and then the first thing that happens to the material is that it gets compressed in the shock. So that means that it propagates up the Hougon-Yeo adiabatic of the shock wave, that's this bold dashed line here, over point E to point D. So this is then the region of highest compression reached. That's the so-called von Neumann spike. And here the material is heated up enough that reactions start, and this then leads to a heating and expansion of the material. And when the material heats and expands, of course, then it will change its conditions here. So the reactions in this ZND model, however, are not assumed to be instantaneous anymore, but with finite range behind the shock. So that means that the material will, due to heat release, expand, and it does so going down a Rayleigh line, because mass and momentum are still conserved for our intermediate states. So it actually, the idea in this model is that we start from an initial state, we get a compression by the shock wave until the material is hot enough in the von Neumann spike to start burning, and then it will expand down a Rayleigh line and finally reach the final state C here on the detonation adiabatic. A special case is the so-called Chapman-Newgate detonations. So here we have the case that we start again in our initial state, and then we go up the detonation, the Hougon-Yeo adiabatic for the shock wave to point E, and then down from this von Neumann spike to the final state on the detonation adiabatic. And if this point that we reach here is the Chapman-Newgate point, which is actually just the point that is reached by a Rayleigh line that is tangential to the detonation adiabatic, then one can show with some arguments that I cannot actually do in detail here that this corresponds to a detonation that propagates sonically with respect to the burned material. And this is actually a particularly stable configuration that is often realized in nature. So quite often we have detonations propagating in this Chapman-Newgate mode. So what about detonations of white dwarfs? Well, they unfortunately diverge from the Chapman-Newgate picture at high fuel densities, and this is because in the reactions endothermic parts are involved when reaching nuclear statistical equilibrium at high fuel densities. Photodisintegrations are endothermic, and therefore this changes the picture of detonations slightly. So we don't have Chapman-Newgate detonations then, but detonations of so-called pathological type, and only at lower fuel densities, when we have incomplete burning to intermediate mass elements, then the detonations become of Chapman-Newgate type again. Okay, again, what about the multi-D picture? Well, detonations are supersonic, so you would not expect them to be subject to external instabilities such as Rayleigh-Taylor or Kelvin-Helmholtz instabilities. However, real detonations still possess a multi-dimensional, three-dimensional structure. The reason for this is that planar detonations are unstable. They form a number of features: incidence shocks, transverse shock waves, and triple points. and the continuous interaction of these features in the detonation propagation in the end leads to a cellular pattern of a detonation. So this is actually something you can get out of numerical simulations on a microscopic level of detonations. So you find something like here in the simulation that was performed by Frank Timmis for a carbon detonation under conditions of that are typical for detonations in white dwarfs. And you have a rather complex structure here. These that consist of incident shocks and forming triple points here. And in these triple points, the compression is higher than in between the triple points. So therefore, in these triple points, the reactions are more complete than in between. And in the end, this leads to an inhomogeneous structure behind the detonation in terms of ash composition and also energy release. But this is an effect that takes place on rather small scales. This is far from being resolved in current multidimensional simulations of thermonuclear supernovae. So the argument you can still make is that this 1D picture we had developed of planar detonations before still applies in an average sense, and this is an acceptable approximation for the real structure. The effect, however, is that in total burning will be a little bit less complete and slower in these detonations if you consider the multi-D structure, but this effect is small at high field densities and becomes more important at lower field densities. But this is something that's currently not treated in multidimensional simulations of thermonuclear supernovae. Okay, nuclear burning in type 1a supernovae. I think, should I stop now or?
It's only 55 minutes.
Yes.
You can.
I have another, I don't know, 10 to 15 slides, 10 slides perhaps.
You can just do part of it.
I can just do it, and I mean, we don't have a lecture after coffee anyway, right? Yeah. So just, okay, so I wanted to switch topics now a little bit and take a closer look at the actual nuclear reactions in type 1a supernovae. Unlike the conditions we find in stellar evolution that you may be more familiar with, in thermonuclear supernovae, nuclear reactions are not proceeding in hydrostatic equilibrium. Instead, what we have is that the energy release is on timescales that is on the order or smaller than the dynamical timescale of the setup. So that means that they drive dynamical effects. The reactions are also not fixed in space, as we discussed just before. They propagate as combustion fronts, and reactions, therefore, by this propagation, occur in a rapidly expanding material because the reaction fronts propagate down a density gradient. They are ignited in the center of the star and propagate down to lower field densities. And in case of subsonic deflagration fronts, the material also expands before it's reached by the deflagration front due to the heat release, and this again leads to the detonation, the combustion wave reaching lower and lower field densities subsequently. So they propagate down at the density gradient in the exploding star. Now that means that we have changing thermodynamic conditions and that these give rise to different burning regimes, nuclear burning regimes. And this is actually the feature that makes thermonuclear explosions of white dwarfs a candidate to explain type 1a supernovae. So that's exact this feature why we think, or one of the reasons why we think we can explain type 1a supernovae with thermonuclear explosions of white dwarfs. The reason is that from the spectra of type 1a supernovae, we can deduce the composition of the material that's produced by the explosion, and we see intermediate mass elements such as silicon here in green and sulfur here in purple, and iron group elements that are shown here in blue. And this can be explained by our picture of a combustion wave propagating down a decreasing fuel density gradient, because at the highest densities near the center of the white dwarf star that explodes, we will reach nuclear statistical equilibrium and iron group elements will be formed in the end. Then if we go down to lower densities, burning becomes incomplete, and intermediate mass elements such as silicon, sulfur, and calcium are produced. At even lower field densities, we have burning from carbon to oxygen, and below a certain threshold, density threshold, burning ceases. And we are then left with unburned material, which can also be detected in spectra of type 1a supernova, but it's much harder to see and more indirect. Now, the explosive burning regimes can be characterized according to the thermodynamic conditions that are reached in the material in terms of density and temperature. So this is actually a plot that was made by Friedrich Thielemann a long time ago in 1986 for this famous W7 one-dimensional thermonuclear supernova explosion model. And the nice feature of this plot is that it actually has marked all the important burning regimes here. So at low densities, so this is density at low densities and rather low temperatures, we have explosive neon and carbon burning. At slightly higher densities, explosive oxygen burning is reached, and then at even higher densities, silicon burning is reached, and then above a certain threshold, we burn to nuclear statistical equilibrium. Now, this is a picture that fits well the observations. As mentioned before, you can actually do this in some more detail. If you neglect all mixing processes due to hydrodynamic instabilities, this sequence of different burning stages by reaching lower and lower fuel densities, of course, produces a radial structure in the chemical composition of the ejector. So we will have in the center iron group material, because burning that took place at the highest densities, and this is surrounded by a layer of intermediate mass elements, and the outer layer you may have unburned material. Now, this is actually seen in real type 1a supernovae. You can deduce from observations the chemical structure of the ejector. The reason why this is possible is that in the supernova explosion, the ejector, of course, slowly expands. And in the first days, the spectrum you see originates only from the outer layers because the inner parts are still optically thick. And as the ejector expands, you look in deeper and deeper. So that means if you take a sequence of spectra every night of a supernova, you do something like a tomography of the abundances. So if you analyze the spectral features and derive the composition, you probe deeper and deeper layers in the ejector by taking spectra every night after the explosion. And this is called abundance tomography, and a result of such an analysis of our abundance tomography is seen here. So what you actually have is that indeed in the inner part you have iron group material that's shown in green and red here. So this is stable iron in green and nickel 56 in red, and then in the outer parts you have intermediate mass elements, and in the very outer parts unburned material. Okay, now I wanted to say some more words about a particularly important effect, and this is actually the burning at the highest densities, and consequently burning reaches the highest temperatures, and in this case nuclear statistical equilibrium is established, and this is actually in large parts the reason why nickel 56 is produced and why we actually see type 1a supernovae as bright astrophysical events, astronomical events, and why they produce iron 56 in the end. So this is important to consider. So we look into the regime where the density are highest and where we reach sufficiently high temperature. So if temperature gets high enough, then a detailed balance between the strong nuclear interactions will establish. Not necessarily the weak ones, but the strong nuclear reactions will be in detailed balance. So we consider some nucleus with a certain number of nucleons in it and a certain charge number in it. So Zi is the number of protons in that nucleus, and Ni, which is Ai minus Zi, is the number of neutrons. And this nucleus has mass Mi, so that we can then write down an expression for its nuclear binding energy, Qi, that is given as the sum of the masses of the protons plus the mass of the neutrons minus the mass of the bound nucleus times c squared. So this gives you just the binding energy, but from the mass defect. Now, at high enough temperatures, the reaction from this bound nucleus to disintegration into its constituents, into protons and neutrons, with all its possible intermediate steps, is in equilibrium with its back reaction. So then one speaks of nuclear statistical equilibrium, and this nuclear statistical equilibrium uniquely fixes the composition for a given set of thermodynamic variables for temperature and density and composition. So if you have given the values of density, temperature, and the mean number of electrons per baryon, YE, then the composition of material and nuclear statistical equilibrium is uniquely determined. And this is because the equilibrium conditions set a condition for the thermodynamic, or a relation for the chemical potential. So the chemical potential of the bound nucleus I is equal to charge number times the chemical potential of the protons plus Newton number times the chemical potential of the neutrons. Now, the chemical potentials, in principle, have different contributions. The dominant contributions are due to rest mass and kinetic energy of the particles. And in the case where we are in the non-degenerate, in the case we are looking at in thermonuclear supernovae and white dwarfs, the nucleons and nuclei are heavy particles, of course, and therefore they are not degenerate, they are not relativistic. So the non-degenerate, non-relativistic approximation, the statistics that follows from this, the Maxwell-Boltzmann statistics, is a good approximation for these. So that means that the kinetic part of the chemical potential is determined by the Maxwell-Boltzmann statistics. So we can actually give from the Maxwell-Boltzmann statistics the chemical potential, the kinetic part of the chemical potential, as a function of particle number density. And this, together with the relation for the chemical potentials, as written up here, determines the mass fractions of all species in nuclear statistical equilibrium in terms of the chemical potential of the protons and the neutrons and the nuclear binding energy of this nucleus I that we consider. This is given by this relation here, which is similar to a Saar equation. Now, this relation has to be fulfilled under constraints, and one constraint is, of course, that for the total composition we have to require that all the mass fractions in the material add up to 1, and that the composition that we achieve in the end must have the prescribed, previously specified mean number of electrons per baryon, the mean YE. From the relation, one can see that as temperature goes up, the composition will shift towards lighter species, and as temperature goes down, the composition shifts towards the species with higher binding energies, the bound nuclei. So this is equilibrium conditions. And now as the white dwarf material expands, we reach lower densities and the temperature will drop. And if the temperature drops below something like 5.5 gigakelvin, then equilibrium is no longer maintained. So the reactions are not in equilibrium anymore, forward and backward reactions, so reactions are not in equilibrium anymore. They fall out of equilibrium, and then the composition changes differently from what the equilibrium relations would predict, and then one has to follow this with a full nuclear reaction network. And this is called freeze out from NSE. It's illustrated here. So the NSE compositions are given for different species, color-coded here as these dashed lines, and the real change of the composition is given with the solid lines. And you see in the beginning at high temperatures these are equal, so we are still in nuclear statistical equilibrium, and for temperatures below 5.5 gigakelvin these diverge, so we fall out of nuclear statistical equilibrium. Now, why is this important? Well, as long as we are still in nuclear statistical equilibrium, the composition is determined by the thermodynamic conditions. For high entropy, we have predominantly light particles, protons, neutrons, and alpha particles. For low entropy, we have bound nuclei. Now, then, depending on how the freeze out from nuclear statistical equilibrium, under which conditions it happens, whether it happens under high entropy or low entropy conditions, we have different kinds of freeze out. At high entropy conditions, the freeze out material will still contain lots of light particles, so the light particles are abundant, and this is called the alpha-rich freeze out. If freeze out from nuclear statistical equilibrium happens under low entropy conditions, then we have so-called normal freeze out from nuclear statistical equilibrium, and the bound nuclei are favored, and we don't have light particles being so abundant. And this is actually important for nuclear synthesis effects that I will discuss on Saturday probably, that allow us to distinguish between different scenarios for thermonuclear supernova explosions. So the very last thing I wanted to mention, it's only 2 or 3 slides left before Chris is up for talking, is a metallicity effect. Nuclear statistical equilibrium composition, as we stated before, depends on the YE, on the mean number of electrons per baryon. So the electron fraction therefore determines which iron group species is predominantly produced in the freeze-out from NSE. And if we have symmetric material, if we have YE being 1/2, the same number of neutrons and protons in the nuclei, so that means that we have 1 electron per 2 nucleons, and YE is 1/2, then the production of nickel-56 is favored. And this is because nickel-56 is the iron group nucleus with the highest binding energy per nucleon under the constraint of being symmetric, having the same numbers of neutrons and protons. So if we actually have NSE under conditions of YE being 1/2, then in the freeze-out we will predominantly produce nickel-56. And this is the case in thermonuclear supernova explosions of white dwarfs, because the material we start out with is carbon-12 and oxygen-16. These are symmetric nuclei, and therefore we don't diverge much from YE being 1/2 and produce nickel-56 abundantly. And this sets, as we discussed in the first lecture, the brightness of the thermonuclear supernova explosion. However, there is an effect of the metallicity of the progenitor star. So this actually gives you one of the very few rather direct implications of the structure of the progenitor on what you see in the explosion. So therefore it's an important effect. The metallicity effect on the 0H main sequence progenitor of the white dwarf has a significant impact on the YE and the NSE, and therefore on the production of nickel-56. So how does this work? It was pointed out by Frank Timmis and collaborators in 2003. So the idea is that in the 0H main sequence star we have some carbon, nitrogen, oxygen composition, the metallicity that's inherited to the star from the composition of the interstellar material it was formed from. And this metallicity is of course important because it is used as a catalyst in CNO cycle burning, and in CNO cycle burning all this material will be converted to nitrogen-14, because the proton capture on nitrogen-14 is the slowest reaction in CNO cycle burning. Then the next stage is after hydrogen burning we reach in the evolution of the star towards and finally forming a white dwarf, we reach helium burning. And in helium burning we have this sequence of reactions: nitrogen-14, alpha gamma, fluorine 18, beta decay, and then beta plus, then oxygen 18 is formed, and finally oxygen 80 alpha gamma forms neon-22. Now in the end, by hydrogen burning, by helium burning, this means that the nitrogen-14 that is left over by CNO cycling in the hydrogen burning is completely converted to neon-22. Now neon-22, so all the metallicity of the progenitor material is converted to neon-22. And neon-22 is neutron rich. It has a YE of 0.4545. So this is a neutron rich nucleus. So therefore it in the presence of neon-22 in the material, the YE is lowered in nuclear statistical equilibrium. And therefore, this composition then favors the production of neutron-rich stable nuclei instead of nickel-56. And so this metallicity, the more metallicity we have in the progenitor star, the more neon-22 we will have in the material when it burns to NSE. The more neutron-rich we will be in NSE, the lower the YE will be in NSE, and the less nickel-56 will be produced in NSE. So that means the metallicity of the progenitor material in the end reduces the nickel-56 that's produced, and therefore reduces the brightness of the thermonuclear supernova. And that's actually an effect that you can model in simulations. So here is a plot by Claudia Travaglio for a 3D deflagration in the Chandrasekhar mass white dwarf. She has tested initial material with different neon-22 mass fractions and has done nuclear synthesis calculations, and she actually finds that with the metallicity of the progenitor star, you actually really reduce the mass of nickel-56 that's produced. Okay, so that's it for today. Thank you very much for your time.
We need time for a few questions. Doesn't reach.
for the nucleosynthesis expert.
The last point that you just added here, the metallicity effect. I didn't follow things all in detail, but the initial paper by Timmis used still the pre-existing models with the energy generation, which did not have included the metallicity effect. So
Yeah.
my question is, how does this work out if you do it really self-consistent?
Yeah, of course. I mean, if you actually include the metallicity effect into the dynamics of the explosion, you mean, because that actually has an effect on the equation of state, of course. But still, actually, you see that. I mean, this is also not proving this, because this here is actually also done just in post-processing, right? But we actually include different YEs, and still, I mean, the effect is still significant. And the important thing here is, I mean, the effect YE and the Neon 22 has on the equation of state is of course important for buoyancy in the deflagration. But this effect also works if you have detonations, right? I mean, if you, and this actually, the dynamics does not change then at all, because you don't have buoyancy effects and you still can reduce the brightness with the YE.
More general question. You showed this example for detonation that the flame was more extended. Is this a general feature?
Oh, the multi-D structure of the detonation?
Yeah.
Yeah, that's a general feature. So detonations look like that. There's even people arguing whether detonations work in multi-D at all. So a detonation, I mean, all the theory we have on detonations is a 1D theory. There's no multi-D theory on detonation ignition and detonation propagation really existent. And so therefore, this is a rather complicated topic. And in multi-D, actually, it may even be that you have this complicated cellular pattern with the triple points. It may even be that some people actually explain it that way, that only in a triple point the shock actually is strong enough to really lead to reactions, so that the detonation is quenched in between. It's always reignited in the triple points, and this is actually how it propagates. So rather complex internal structure of multi-D detonations. Yeah, and I think engineers probably look into this. This is all not accounted for in multi-D simulations of the nuclear supernovae, because this structure is actually much below the scales that we can resolve. But it may actually be important in the low density burning. Then the cells get larger, and then of course if you are in incomplete silicon burning or so, then this may be important. It may actually even lead to chemical inhomogeneities of the ejector, in cases where you have a detonation and by a naive picture would expect a very clear stratification of chemical stratification of the ejector, but the multi-D effects may still change this picture. Okay.
So what's the typical size of the detonation cells in Timmis simulation?
Well, it depends on the density, right? And he did it, I think, only for one fuel density. And you can look it up in the paper. It was very small compared to the scales that you have in the white dwarf. So that's why his conclusion was the effect is not very significant at the high fuel densities. But of course, it may be different at low fuel densities.
What about the typical scale of Rayleigh bubbles I think in former slides? You showed the simulation of Rayleigh and Kevin Helford.
Yes. So the scale of the scale 10 to the 7 centimeters or something like that. So I mean the scale is large. I mean if I will show simulations of deflagrations in Chandra-Sekhar white dwarf, and what you actually see is sort of a few larger plumes that actually maybe 4 or 5 that actually cover the entire volume, but then they have again smaller cells above each other and a more complicated structure. So that you have actually sort of this buoyancy instability acting on various scales.
So it is about 700 centimeters. The largest
is a fraction of the entire white dwarf. It's hundreds of kilometers.
Oh, it can be that large.
Yeah.
The last question, maybe?
Well, you got the answer already, but coming back to observations.
Okay. Ask Alicia.
This spectra, for example, so they point to mainly deflagration or detonation regime. So
yeah, I will discuss that on. So the plan for the rest of the lecture is here. I have it on a slide. Can directly show it. Show it. So We'll now discuss some simulation techniques, then progenitors, and then we'll talk about different explosion scenarios. And of course, you have all these possibilities that you have deflagrations, you have detonations in Chandrasekhar mass explosions, in sub-Chandrasekhar mass explosions, you have transitions between these two. And this will be discussed on Friday. And on Saturday, the plan is that I will then discuss the predictions for observables that result from these. And on this basis, we try to actually sort of nail down which explosion process is really acting in Japanese supernovae, but this will be discussed on Friday and Saturday.
So let's start.